Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Glad to be here.
Okay, let's fire up the machine. We are jumping into a deep dive today on the literal components that make our industrialized world spin. Machine element design and mechanisms.
That's right. And we've compiled sources that, they really skip the abstract theory.
Yeah, this is all practical stuff.
It's pure, practical, tested design data, the kind of knowledge that comes straight from major manufacturers.
So our mission for this deep dive is to extract that high leverage knowledge. We're talking about the procedures, the safety margins, all the non-negotiable physical laws for designing complex systems.
And then we're going to focus on power transmission, shafts, and, of course, everyone's favorite, gearing.
It's funny because no matter how complex the final machine is, it always comes back to the basics, doesn't it?
It always does. The foundation is still the simple machines. I mean, the lever, the inclined plane, which gives you the wedge and the screw and the wheel and axle.
The pulley, the gear wheel, all that.
Exactly. And, there are some modern additions people talk about, like the hydraulic press.
And what was that other one? The Rollamite device?
The Rollamite, yeah. It was, I think the U.S. Patent Office actually declared it a new simple machine some years back. It's fascinating.
But for us, today, we're sticking to the industrial workhorses.
Absolutely. We're talking about the precise standards and constraints for components that have to run, reliably for decades. You need to know it will perform exactly as you calculated.
Okay, let's unpack this. Power transmission fundamentals. Let's start with belts. A lot of people mix up sheave and pulley.
They do, and it's a critical distinction, really. A sheave is the grooved wheel. It's specifically for V-belts.
And a pulley.
A pulley is, well, traditionally it's the wheel for a flat belt. It's a simple thing, but mixing them up sort of signals you don't grasp the underlying physics.
Speaking of V-belts, we have the classic sizes A through E, and then the narrow V-belts, the 3V, 5V, 8V.
Right.
Why do designers go for the narrow V-belts when they need high power?
It's all about power density. The narrow V-belts are just engineered better for the job. The load from the belt's tension cords gets transferred much more directly to the sides of the sheave grooves.
So it's a more efficient transfer of force.
A much more efficient transfer.
Yeah.
So for the same width, a narrow V-belt gives you a significantly higher power rating. You just get more work done in less space.
And the actual work, the horsepower, comes from the pull, right? The difference in tension between the tight and slack sides.
That's the core of it. And you can't just design for that. You have to check your geometry. The designer has to calculate the arc of contact correction factor. We call it G.
Okay, what happens if you don't?
Well, if your belt doesn't wrap far enough around the smaller sheave, your arc of contact is too small. You lose load carrying.
Capacity. And it starts to slip.
It just slips. You have to account for that reduction in your design.
And I'm guessing speed is a hard limit here.
Oh, absolutely. Friction is heat, and centrifugal force is trying to pull the belt right off the sheave. So designers have to keep narrow V-belts below 6,500 feet per minute.
And classic V-belts.
Well, a little lower. Below 6,000. If you go past those limits, you're just guaranteeing failure. And a dangerous failure at that.
Okay, let's shift from belts to chains. Roller chain. It's super reliable, comes in riveted and detachable types. But the real decision seems to be the sprocket.
That's where the budget meets the road, so to speak. You have to choose a commercial sprocket or a precision sprocket.
So when do you have to spend the extra money for precision?
Anytime you have high speed, high loads, fixed centers, or the big one, any application that needs accurate timing.
Like for registration marks on a printing press or something?
Exactly. If your machine needs that chain to be in a very specific place at a specific time, you need the manufacturing tolerance of a precision sprocket. Commercial sprockets are fine for, say, a farm implement, but not for that.
This is where the source material got really interesting. It gave a pretty serious warning about quality control.
It did, yeah. The sources stress that while U.S.-made roller chain is generally up to spec, ANSI and ASTM standards imported chain needs very careful inspection.
They actually compared it to counterfeit hardware.
Yes, like bolts and screws that say they're a certain grade but fail way below their advertised strength.
That is terrifying. You could design a whole system based on the strength of a component, and if the part you bought isn't what it claims to be.
The whole thing fails catastrophically. It's a huge liability. It just means you have to be so diligent about where your parts are coming from.
Yeah.
Your design is only as good as its weakest link, literally.
Let's move to the backbone of all this. Shafts. The structural spine of rotating machinery. and they're under a whole cocktail of different stresses.
That's a good way to put it. You've got your bending and torsional stresses, sure, but the real design constraints are usually the deflections.
So angular and linear deflection.
Right. Torsional deflection and what we call delta X. And then there's the big one, the operational limit. Critical speed. We'll get to that.
First, deflection. What's the practical hard limit when a shaft is carrying something that has to be stiff, like a gear?
Okay, so for gearing, stiffness is almost always more important than raw strength. The rule of thumb, the recommended max, is an angular deflection of no more than 0.08 degrees per foot of length.
0.08 degrees. That's tiny.
It's incredibly small.
Huh.
But if you violate it, you guarantee massive misalignment in your gear teeth. They'll just chew each other up. Your bearings will fail. It's a non-negotiable threshold.
And you have a great example that shows how geometry can totally overpower material strength.
We do. So take a standard 1¼ inch diameter shaft. It's supporting a 400-pound load. The calculated linear deflection, the delta X, was 0.0302 inches.
30 thousandths. Sounds...
Still a layman, yeah.
Okay.
But for a gearing application, that's completely unacceptable. That runout would destroy the system.
So you can't just use a stronger steel.
No, that's the point. The solution isn't a stronger material, it's a stiffer geometry. You have to make the shaft diameter bigger or move the support bearings much closer together. Geometry dictates performance here.
Once you have the geometry, then you can talk materials. Medium carbon steels like 1045 are common, but they need heat treating. What about those specialized high manganese steels?
Things like stress-proof and fatigue-proof. They're metallurgical magic. They get their incredible strength. We're talking 100,000, even 125,000 psi yield strength from severe cold working.
And the big advantage is...
no heat treatment. That's a massive win. It saves money, simplifies manufacturing, and crucially, it prevents the distortion and warping that you so often get with long heat-treated shafts.
a fantastic trade-off. But what if your shafts just can't be in line? That's where the hooks coupling comes in, right? The universal joint.
The Cardan universal joint, yeah, it's the standard solution, but it has a major inherent flaw.
Which is?
Non-uniform angular velocity.
Meaning the output shaft speeds up and slows down with every single rotation, even if the input is perfectly steady.
Precisely, and it's not a small effect. Let's look at the numbers. Say you have a driver shaft at a constant 250 RPM, and the joint angle is 23 degrees.
Okay.
The speed fluctuation on the driven side is 41.5 RPM.
Wow, that's huge.
It's massive. That variance creates severe vibration and wear on any system trying to maintain smooth motion.
So what's the fix? How does the designer get around this?
You have to use two of them, two U-joints with an intermediate shaft.
Oh, okay.
But the alignment is everything. The main driver and driven shafts have to be parallel, and the forks on that intermediate shaft must be aligned in the same plane. The first joint creates the variation, and the second one perfectly cancels it out.
As long as it's set up correctly.
As long as it's perfect, yeah.
Let's get into controlling motion clutches and brakes. The sources lay out two major categories.
Yep. You have your positive clutches, which use interlocking teeth. They're for hard, reliable engagement. And then you have the workhorses, the friction clutches.
Disc, cone, centrifugal, all those.
All of those. They just rely on friction surfaces to transmit torque.
And for those, the goal is to prevent slipping. What kind of safety margin do the sources recommend?
You can't just design for the maximum torque. The coefficient of friction changes with heat, wear, contaminants. So you need a buffer.
The safety factor.
Exactly. The slipping torque capacity of the clutch needs to be greater than the driver's max torque, multiplied by a safety factor of, say, 1.40 to 1.6 here. That guarantees it will hold.
That's the engineer's insurance policy. Now, when we're calculating for clutches and brakes, the key variable is inertia.
Inertia, yeah. The fundamental calculation is WR squared.
Weight times the radius of gyration squared.
Right, and it's absolutely critical for one reason above all others. Heat dissipation. When you stop a mass, all that kinetic energy has to go somewhere. It becomes heat. The clutch or brake has to be big enough to soak up that thermal load without failing.
But at a big machine, you have parts spinning at all different speeds. The clutch is only at one speed. So how do you account for all that energy?
That's where you get into the concept of reflected inertia.
Right.
It's like kinetic energy accounting. You mathematically reduce the inertia of every moving part, the fast fan, the slow conveyor down to an equivalent WR squared value at the speed of the clutch shaft.
So you can add it all up.
You add it all up, it gives you the total energy the clutch has to manage. If you miss that step, your heat calculations are wrong, and your component will cook itself.
It's the only way to size your heat sink properly. Okay, let's pivot to power screws, jack screws.
Used for lifting, clamping, they use square, Acme, V-threads. And the number one calculation priority is estimating the surface bearing pressure on those threads.
To make sure they don't shear off.
Exactly.
Yeah.
And just like with clutches, the simple first-pass equation isn't quite good enough.
It needs a safety factor.
It does. The simple formula tends to give you an underestimate of the real pressure. So you have to apply a safety factor, maybe 1.25 to 1.35, to get the final safe pressure you designed for.
Okay, let's dive into the final and maybe most complex topic, the world of gearing, starting with the most common, the spur gear.
The spur gear. And the magic behind it is a very specific tooth shape called the involute profile.
And that's essential for what?
For uniform angular velocity. It's a mathematical curve that ensures speed transfer stays perfectly constant and smooth, even if there are slight errors in the center distance between the gears.
The big choice a designer has to make here is the pressure angle, or PA. Usually 14.5 degrees versus 20 degrees. What's the trade-off?
It's a classic strength versus smoothness debate. The 14.5-degree gears are smoother, quieter, and a bit more forgiving of alignment errors.
Good for precision?
Great for precision, but the 20-degree PA gears are just stronger. They have a higher load-carrying capacity, hands down.
But there's a catch, isn't there, if you use too few teeth?
There is. It's called undercutting. If you design a 20-degree PA gear with, say, fewer than 18 teeth, the manufacturing process actually starts to remove material from the base of the tooth.
Weakening it.
Right at the point of highest stress. So you gain strength from the angle, but lose it all back by trying to make the gear too small.
And all of this is based on the Lewis equation.
The Barth revision, yeah. It treats the tooth like a simple cantilevered beam. It's still the foundation.
Okay, what about helical gears?
Helical gears are for parallel shafts, and you have to pair them right. A left-hand pinion needs a right-hand gear.
And the big advantage over a spur gear.
They're much quieter because the teeth engage gradually. They also have better tooth strength and a much greater load capacity for the same size.
But there's a downside.
A big one. The angled teeth create an axial load, a thrust load, and that force has to be absorbed by thrust bearings. If you don't spec the right bearing system, the whole assembly will tear itself apart.
Got it. Let's talk worm gearing. These are for really specialized jobs.
They are. They're perfect for three things. Huge speed reduction in a tiny space, transmitting high torque at a right angle, and resisting backdriving.
Meaning the output can't easily turn the input.
Exactly.
And that extreme ratio comes from.
It's the number of teeth on the worm wheel divided by the number of leads on the worm itself, which is usually just 1 to 4.
But there's a catch with the torque output, right?
A crucial one. The output torque isn't just input torque times the ratio. You also have to multiply by the efficiency. There's a lot of sliding friction, so you lose a significant amount of energy as heat.
The sources mentioned a bunch of other specialty gears.
Yeah, Zerol, bevel, hypoid, spheroid. The spheroid gears are worth remembering. They're known for combining a very high ratio with a compact design that's cheap to mass produce.
Okay, let's end the design talk with the most practical tool of all. You're in a shop, you've got an old gear, no documentation. How do you figure out what it is?
You need a gear tooth gauge.
Simple as that.
It's a simple tool. It's like a set of templates. You use it to physically identify the diametral pitch, how fine the teeth are, and the pressure angle, 14.5 or 20 degrees. You just match the profile. It's the designer's decoder ring.
This has been fantastic. It really shows how every single component, from a V-belt to a gear, is governed by these incredibly detailed design constraints and safety margins.
Absolutely. We've talked about systems limited by heat, by stiffness, by material stress. But if we tie it all back to the foundation, the shaft, there's one constraint that can override everything else, and it's a powerful final thought for you, the designer.
And that would be the dynamic limit.
That would be the importance of critical speed.
Okay.
For any given shaft with its diameter and length, there is a specific RPM, the first critical speed, where it becomes dynamically unstable. It starts to whip like a jump rope.
Regardless of how strong the material is.
It doesn't matter how strong the steel is. The calculation shows that the ultimate performance of a rotating system isn't limited by its static strength, but by its structural dynamics.
So structure beats strength.
In high-performance design, structure almost always beats strength. It's a critical trade-off you face every single day.
Dynamic stability over static strength. A perfect note to end on. Thank you for tuning into this deep dive.
Until next time.